let's see. Oops. Yes. Yeah. אוקיי. כן, חם פה. אני חושב שאפשר לעשות פעולה בנושא. אלוהים נגיד נדליק את המזגן, אולי זה יעזור.
פעם היה את האל הזה שדיברת עליו.
מה זה?
הטכנאי, לא? חשבתי זה רק הוא יכול לעשות את הפעולה הזאת.
יש קורס הזה באוניברסיטה שאפשר לעשות.
כן.
אוקיי. רק אנחנו לא רוצים 16 מעלות.
משהו שאפשר לעשות עליו קורס.
אולי 23 זה מספיק.
שיטות ניסיוניות?
יופי, נו, 14 מעלות פה. Okay. Hopefully this will improve the weather. And about the question, apparently somebody has had courses with me before, and there are things. This air condition works on water. So actually what it does, it's not real air condition, there's a cold water running in the entire building. And this is just a heat exchange. So the, what?
Are we a computer or something that we need water cooling?
Well, you know, most computers are only air cooled. But yeah. So this is important in quantum optics. Listen very well, very carefully, because this is yeah. So yes. So this entire building runs on water. But the point is that there's only one pipe of water, and this pipe can either run cold water or hot water. You don't know which. Well, it means that in the summer, it's most likely running cold water, unless somebody completely forgot. And in the winter, it's likely running hot water. Therefore, it can only do one thing: either cool, if the water is cold, or heat, if the water is warm. And so if you just tell it from here cool, if there's cold water, it will. If there isn't, it will just do nothing. So, yeah. So that what it means is that you can turn it on and hope that the water is running, and then it will cool. And if not, then not. Yeah. But the nano building is much more advanced. You have two pipes.
Whoa, that's crazy.
So, yeah, one is running hot water all through the year. What? Yes. Well, actually, it's a much better, in terms of efficiency, it's much more efficient to have a central cooling device that generates a coolant, can be water or anything else, and assuming that the pipes are sufficiently isolated It is much more efficient than having many small air conditions for every room. If we discuss this, and again, this is very important in quantum optics, probably the most efficient way to both cool and heat, well, you know that, for example, an air condition is more efficient than, even in heating, than just a resistor. Because a resistor transforms energy, electricity to heat. And an air condition uses the electricity to transfer heat from the outside into the inside. So an air condition is a heat pump, whereas a resistor, or just, a stove, is just a heater. Now, the point is that a heat pump, works best when the two temperatures are very similar. I mean, it's very easy to transfer water between two lakes that are at the same height. But when there's and you can consider the temperature difference as a height difference. So the air condition must work harder once the temperature difference grows. This is, for example, the reason why in Siberia they don't use air conditions to heat in the winter. Because you don't gain anymore when the temperature difference that you want to keep is 60 degrees or something like this. If the outside is minus 50 and inside you want plus 10, because they're Russian, so for them plus 10 is warm. And then, but here in Israel it does make sense to use an air condition to heat in the winter, because the outside temperature doesn't go too low. It would have been it would have been better if you could work against a reservoir. What is the reservoir that you work against? You're trying to cool the inside, and you're using the outside as your reservoir. So, but if you had a reservoir of a temperature which is very similar to what you want to keep inside, that would have been the best. The problem is that, well, sometimes it's 40 degrees outside, and you don't want to be in 40 degrees inside. So, what can you do? The answer is drill a deep hole in the ground. If you you do it
in 2 stages.
So the earth, or the soil, something like between 10 or 20 meters below the ground, has an almost completely stable temperature of around 22, 23, 24 degrees. So if the next time you're building a house, you should consider, I don't remember how they're called, but those systems, they cost $1 million. They need to be installed in advance, because before you need to prepare before you build a house. I mean, you need to drill and put in some heat exchange, and usually it's more than one, because the ground is not very good heat conductor. So you need to put several of them. So, and then run water through, and then the water will come back at the temperature of the ground, and now make a heat exchange again. This would be and then that's the most efficient air condition you could think. Exactly. It's like a double state. Yeah, that was part of the quantum optics. Where do you think I know that from? Well, As these two guys know, I'm quite tired today, so I'm not exactly. We're going to talk about coherent states, but it's not so clear if I will be in a completely coherent state. So, so yeah, maybe we'll waste the time speaking about air conditions and maybe cameras and cooling and vacuum pumps and things like this. But no. Okay. So, last week, we talked about we started talking about the beam splitter and about transformations of states. What happens when we go from, we were talking about all kinds of elements that do a mode transformation. What are those? One of the simplest one is a beam splitter. A beam splitter is an example of how you can take two incoming modes to generate. So yeah, we're talking about what to do with mode mixers. The example was a beam splitter where you have two incoming modes, 1 and 2, and you have two outgoing modes. And classically, we know to write, and this has some reflectivity R and transmission T, so we know that to write that, for example, E3 equals R E1 plus T E2, and E4 equals what? T E1 minus R E4, E, I don't know, 2. And what I told you last time, well, this is classical. Why should it be? What's going to happen quantum mechanically? That's simple. You put hats on this. Those are, the relations remain. As I told you, think of it in this way. The mode is a classical entity. The field in that mode, the amplitude of the field within this mode, is a quantum one. That's the quantum. But this didn't change. This is the field in mode 3. This is the field in mode 4. And they're related to the fields that came and hit the beam splitter in modes 1 and 2. So the quantum transition is simple, just do this. Or, in other words, as we know, the field operator is, for a specific mode, is the creation and I think that this one, this is not so great. Let's try another. So all we need to do now is just to say that this relation holds for the creation and annihilation operators. So yeah, and you know, when we write this, we mean here basically the slow varying amplitude of the field. So now I'll do what I can, and that is to just say, look, instead of the field, well, I'll write here the creation and annihilation, or the annihilation operators. I don't know. Okay. So, and this is a common trick. This is something that we do a lot. And now that means that we can Now things are nice, because now we can say, okay, tell me what comes in here, and I'll make calculation on what comes out. We gave an example. Suppose that we have here a coherent state, maybe, and here there's vacuum, so that, you know, I can say that the state psi is what? The coherent state in mode 1, and vacuum in mode 2. And now, well, you know, I want to calculate the output. So suppose I want to calculate the average number of photons in mode 3. And tell me whatever you want to calculate. You can calculate the average number of photons. You can calculate any higher moments of the number of photons. Let's do that just for practice. So I can say, okay, so I want to calculate the average N3. What does that mean? That is the average of A3 dagger A3. This is counting how many photons are there. Well, that's fine. I should do this. And, well, I'll ask myself, well, I know what the state is, but it's not in the language of A3. It's in the language of modes 0 and 1. So what I can do is I can translate A3 back to the language of A1 and A2 using this. So that will be, and I'll have here alpha on 1 and 0 and 2. And then there will be here what? R. Let's assume R and T are real numbers, just so I don't need to put stars everywhere. But normally I would put here, of course, R star A1 dagger plus T star A2 dagger, and here would be R A1 plus T A2, and then here same thing, alpha on 1 and 0 at 2. And okay, now if we wrote it, then we'll keep it, and then we can open these guys, but clearly the only operator that will do anything here will be the A1 dagger A1, because everything else will operate somehow to generate 0. Do you see it? Or good.
A2 will kill from the right, A2 dagger will kill from the left.
Right.
And that's it. That's all it is.
Well, actually, yes. The only thing that can survive here is what does not contain A2. So we have here just alpha and then absolute value of R squared A dagger A, and that means that surprisingly the average number will be absolute value of R squared times alpha squared. Surprise, surprise. What?
דגל זה לא הייתה תפילה, כאילו, אז למה A2 לא שורד? קודם בונים ואז עושים לו.
Well, first of all, the daggers are on the back, and so you can operate them to the left, and when you operate a dagger to the left, it is like an annihilation to the right. Is that? Okay. So that was one example, and of course now we can go further. I can ask myself, okay, so what is N3 squared average? That would be a little bit more annoying, because then I will need to calculate the average of A3 dagger A3, and again A3 dagger A3. So we'll need to do the algebra here. It's not going to be nice, but it's just algebra. And I'm not going to do this because I'm too tired and I'm incoherent. And then, of course, for example, we can calculate the noise, which is I'll tell you what this will come out to be. I'll tell you what this will come out to be. This will come out to be alpha absolute value to the fourth plus alpha absolute value to the squared. And this, you already know what it is, it's calculated. So this is alpha absolute value to the fourth. So what we will have out of here is just alpha absolute value squared, which means that the uncertainty itself will be just, or in other words, square root of n3. Well, that's just the fact that the coherent state has an uncertainty of, we'll see that we'll discuss the coherent state, or I'll remind you some properties of the coherent state soon. So, but yeah, so the average number or the fluctuation is of order of a square root, which is a standard property of Poissonian processes or distributions, which is what the coherent state is. So, once we know how to work with mode mixers like this, we can use them for all kinds of things. So now I want to tell you what our plan for today is. So we want to talk about the quantum homodyne measurement. So those are the subjects of today. And you need to be quiet. This makes too much noise. Now then, the problem is, and we want to talk about coherent states. Actually, I want to talk about too many things. So I don't know about how many of them I'll discuss, and we'll understand. The reason I want to talk about coherent state is to understand that those are just shifted vacuum. And yes. Now I want to talk about the Wigner function, at least partially, and hopefully I would like to talk to you also about the squeezed states, or to start talking about squeezing. Okay. So they don't seem to be related, but actually they are. And I hope that we will make the connection clear during our discussion. Now, so I'll start with the homodyne measurement. In a sense, if you remember, we talked about how would I measure we defined, I remind you again, first classically, we define the quadratures of light. So if I have a classical field, which is a single frequency field, then it has some amplitude and a phase, or I can write it as x times cosine omega t plus y sine omega t. And those x and y are just a, in this case, cosine phi, and this one is a sine phi. So we like to say that what we have is a complex field of amplitude a and phase, or we can say that we have a real and imaginary part of the complex field are the quadratures, and they are the cosine and sine. And as we said before, and before we go quantum, how would I measure x or y classically? That's pretty clear. Take another field which has a phase 0 and stable. So it has the same frequency exactly, but a stable phase. Now you could say, how do you know that its phase is 0? Actually, I don't care. This is my phase reference. The absolute phase is never relevant. So I measure relative to this local oscillator. And then, so the idea is, let's look, and then I need to multiply. So suppose here now that I have a local oscillator field, which is a local oscillator times cosine omega t, and only cosine. And if I want to measure x, for example, what I would do is I'll take my field, input field, I'll multiply it by the local oscillator field, and this of course will be a local oscillator outside times x cosine squared omega t plus y, let's immediately write, half sine twice omega t, because cosine times sine is and if I now just average this over a short period of time, then this will be the average of this. And in the averaging, this one will fall, and this will come down to half. So this, when you multiply, and this is called homodyne detection. So this is just half a local oscillator times x. So it is worthwhile to use a strong local oscillator because it will amplify your measurement, especially assuming x is small. Whatever you wanted to measure was weak. So it makes sense to use a strong local oscillator. And of course, if I wanted to measure y, all I needed to do was to move the phase of the local oscillator from cosine to sine, or to change the phase of the local oscillator by 90 degrees. Because everything is measured relative to something. So I decide that this is x. If I want to measure y, then I'll flip the phase by 90 degrees. I'll add 90 degrees of phase, so it will become a sine wave relative to itself. Okay.
So the local oscillator has the same frequency as the field?
Yes. So the local oscillator tells you in which frequency you're measuring the quadrature. Now notice, and remember, so far we assume that A is a number and phi is a number. But you know fields could be time dependent. So x could depend on time, and y could depend on time. What would it do? At least classically here, nothing changes. That's fine. This will now then this thing works. As long I'm assuming now that that x is changing not faster than the frequency itself. I mean, if it changes faster than the frequency itself, then things are just, I mean, it doesn't make any sense. But so we assume that this is a relatively slow envelope. It doesn't have to be very slow, but it's relatively slow, slower than the carrier itself.
It should also be slower than the local.
They're both the same frequency.
It should be
The local oscillator, we assume that is, this one is steady. It has constant phase of 0 and a constant intensity of.
Slower than your measurement.
Yes, but I can look. It is enough to average over a single period of the. You don't need a long averaging time, but it is true that what your averaging time is that dictates how fast of changes you can follow in x. Remember this. So now, okay. So we understand what we need to do with when we want to do a homodyne measurement. And you know what? Let me say a few more things about this. If indeed, as we said, x could be a function of time, but we should remember that this is a real function, and it's the real part of the complex amplitude, which also can depend on time. That's the A of t is the envelope, the complex envelope now. So I'm assuming here that this is A e to the I omega t. Now A became complex. This is the real part of this, where A is the complex number there. So x is and now just a few reminders of Fourier relations. If you have a signal A of t times e to the I omega t, well, if I want to do a Fourier, so if this is the frequency omega now, and this is let's call this omega naught, okay? Then I could, what's the relation between the Fourier transform of A of t to the Fourier transform of this thing? It shifted. Yeah. So the envelope A of t, I don't know if that is A of omega, then the field, if I just multiply by a carrier, it's just shifting this. So if I talk about the spectrum of A or the spectrum of E, they're the same thing up to a shift. Now, okay, good. And then, so I'm telling you things that you know, because soon, surprisingly, those things will be important. Now I can do the same here, but this is simple. If I want to talk about the real part, so this is A of t plus A star of t. This is what x is. So if I want to ask myself, what is x of, now I'll be careful. I want to say of omega, but well, that's fine. X of omega is related, well, we can see it's a of omega plus what's the Fourier transform of the complex it will take a moment to understand that this is this, a star of minus omega. What? Why is there a minus here? No, you should. This is, yeah, a quick reminder. If I want to talk about, so E of t is what? Is the integral d omega, or let's a of t, of course, is the integral a of omega e to the I omega t. Now, if this is star, then the whole thing is star. And then, indeed, first of all, the star comes in here, which makes this star. But the star comes also into here. And this flips the sign of the frequency. So this is mathematically why this is true. Now then, so now you can see that if I want to talk about a time-dependent quadrature, so if it's time-dependent, then that means, no, if something is time-dependent, you can talk about this in frequency as well. And maybe it's interesting. So the time-dependent quadrature, which is measured by a fast homodyne measurement, so assuming that this integration time is short, I can measure x of t with rather fast. The shorter the integration time, the faster changes in x of t I'll be able to follow. And if I want to discuss this in frequency, then I would say, look, this is related to the, indeed, it must be related to the spectrum of A itself. You know, this was to discuss the quadratures or to discuss A of t is the same. So if this had a spectrum, then this one has a spectrum that is related. But what is it? It is the symmetric part of the spectrum. Whereas, of course, if I'll do the same for y, it is the antisymmetric part of the spectrum. So, and y of omega, which is the sign, so this is the imaginary part of this, and this will come out to be a of omega minus a star of minus omega. Maybe there's an I in front, but forget it. Okay. So yeah, like you can see, or maybe it's better to just write it a little bit more. So if I had y of t, which is equals to the imaginary part of A, which is just A minus A star, is there an I in front? Yeah, I. Forget the half. And then, so we'll get that y of omega is just the same thing. So there will be an I here and A omega minus A. So we can say that X is the symmetric part of the spectrum. And now remember something. What is this amplitude, quantum mechanically? It's the creation or annihilation operator. So those can have So we have the results. X is symmetric, it should be a double M. We should go back to Zoom where it's easier to erase. No, we should not. Why? Anti-symmetric part of A of omega. And this is important. And the point is, we don't like to discuss time-dependent fields. When we go quantum, we prefer to work in the frequency domain. So we prefer to work with amplitudes of specific frequencies. It's more convenient because the amplitude of a given frequency is related to the annihilation operator of the field in that frequency. So, so it is more convenient to talk about X at frequency omega is related to the annihilation operator at omega 0 plus omega, and plus, I'm looking here. What is this? This is the shift from the carrier. What is this? This is another shift from the carrier to the other side. That would be a dagger of omega naught minus omega. Which is exactly to say that we look at those two offsets from the carrier. Now, okay. That went a little bit too far, but let's go back to the single mode case, to the case that, don't worry, the field is not time dependent, and you merely need to measure two numbers, X and Y. A is a constant or varies very slowly. Phi is a constant, is varying very slowly. Those two, X and Y, they are time independent, and by doing this, we'll be measuring one of them. So what we want to do is first be able to make a good local oscillator. Now, well, maybe I should have discussed the coherent states first, but as I told you, I'm not completely coherent today. So, and this joke is running out of credit very quickly. Okay, so we're going to basically assume that we have something like this. So what do we need? We need something that will represent the local oscillator, and we need a multiplier, something that will generate an effective multiplication. So I want to be able to multiply two fields. Now, if this was a radio, if you were engineers, of course, I mean, no, I don't want to talk about it. Some of my best friends are engineers, of course. What?
אתה מוקלט?
I know, and I know that there are engineers in the crowd, even now, today. And I'm just, I hope that all the listeners understand that it is a joke. Though I know that whenever the crowd is sufficiently large, there must be at least some who do not understand the joke and get very angry. So, I assume that the number of listeners is sufficiently small that the probability of a non-understander is low enough. But okay. So if you do this in radio, it's simple. You need something nonlinear, some device that has a nonlinear response. It's called a mixer. So really, you take whatever if you have a field, you have a mixer. Now, inconveniently, we use the same word for two things that are very different. And surprisingly, we're going to implement them in a similar way. So if you have an input, but this tells me that I want to multiply. This is a multiplier. So in here I'll have my local oscillator, and really I'll get this here in time. So this will come out, there will be a field coming out of here that is indeed the multiplication of those two fields. So, or if this is in my lab, we have mixers. You take a cable from one source, you take another cable from another source, and you connect them to this simple small element that is a mixer, and you get out a field which is proportional to the multiplication of those two. So we do this really in time, that's simple. And then we just take this and average the result. So now we need an optical mixer. And I will understand why we call them the same. Well, the problem is that okay. So we need something like this. And how do we do this in optics? The problem is that we don't have simple multipliers like that. Actually, we do. In our lab, we do. But this is what parametric homodyne is all about. But I'm not teaching you parametric homodyne right now. So I'm saying it quietly. Nobody heard. So we do exactly what is written there. So we mix the modes. I'll have here an input field and a local oscillator field. And then we know what will happen. We're still in the classical domain. And then here I will have REN plus TE local oscillator. Let's make our life convenient and make sure that this beam splitter is 50-50. So if it's 50-50, and the field here is 1 over square root of 2 times this. And what we have here is 1 over square root of 2 times the difference between them. Now this didn't do yet anything. It didn't do anything yet. But now we're going to put and now what we do is we put detectors. And we take the difference between those two. So that's how standard homodyne works in optics. And I'll explain why. Okay, so if you put a detector, then this detector, there is going to be the intensity I1 and the intensity I2. And it will be proportional to the intensity of that field. Okay? So I1 will be like the intensity. So this will be like E in plus E local oscillator absolute value squared. And this one will go like E in minus E local oscillator absolute value squared. And then you can see that, well, clearly the intensity, we can open this as being the intensity of E in absolute value squared plus the intensity of the local oscillator squared plus twice the real part of E in, I'm sorry, Enimako. So I have to write it again. Twice the real part of E in E local oscillator star. And here, well, there was a half up front. I'm not following all the prefactor. And here it's going to be the same, just with a minus sign. Which means that when we take the difference, we dig out only this element, which is exactly what we want. So when we take the difference, so the idea is have an interference between those two fields, measure the intensities and take the difference. So, or measure, you have really two photocurrents coming from the two detectors and take the difference between them. Where is our multiplier? What is our multiplier?
Correlation?
No. Our multiplier is the detector, because it detects the intensity and not the field. When we took the intensity, that's when we generated the multiplication. Because it's a square law detector, so we're using the fact that our detectors are intensity detectors and not field detectors to act as an effective multiplier. And the point is that this is an unbalanced multiplier, or in the sense it generates additional terms. And if you want to get rid of those additional terms, then what you do is you detect both ports and take the difference. Because the signal that you're interested in is flipped in terms of in sign, and those two have the same sign. So those two are rejected as common mode. Okay, so this is how standard homodyne works. Now, if I want to do something quantum mechanical, eventually everything. Oh, there's one more thing that I want to say. So what I told you is that one, the multiplier is the detector. And the other thing that I wanted to tell you is, what is the averaging time here? Well, it can be anything, whatever I want, but what's the minimum I can do?
Again, what is the question?
I'm asking, in this kind of measurement, what dictates the minimum averaging time? So if you remember, in a homodyne measurement, I want to average over a short time. It needs to be at least one period of the field. And basically, that's enough. I mean, just average over one period of, and that's it. You have the detection. But of course, it can be longer. What do you think dictates in this kind of measurement the minimum averaging time possible.
הזמן שהחיישן עושה, הממוצע שהחיישן עושה.
Thank you, David. Okay, so this has an integration time. The detector has some integration time. So the minimum or like averaging time equals detector integration time. So, and here comes one of the major limitations of standard homodyne, at least in optics. That is that those detectors are unfortunately slow. They never have averaging times of the order of a single period of the field. They really have. So a single period of the field, let's remember the wavelength. The wavelength is about 1 micron, which means that the frequency is about 300 terahertz, or several hundred terahertz anyway. Which means that the period in time is about 3 femtoseconds. Maybe 2, maybe 5. I don't really care. So 3 femtoseconds. The integration time of the fastest detectors we can think of are nanosecond. I'm saying this for a reason. There are faster detectors. You could have detectors that operate at 100 pico, 20 pico even, 10 pico. Those are really, it's tough to build a detector that is so fast. And we can see that there are at least some or a few more orders of magnitude to go to the femtosecond regime. And I said that it's a nanosecond or less because you need, the question is what would limit your measurement sensitivity? How small of a signal can you measure? Well, one thing that would limit it is the strength of the local oscillator. If you can make a stronger local oscillator, it's always better. But at some point, you burn the detectors or something like this happens. So there are limits to how high you can take the local oscillator intensity to. The other thing that limits it is the detector noise. Because, you know, what are we doing? We have 2 independent detectors that are measuring the intensity of light, and we take the difference between them. So if this one has noise, the other one has different noise, and therefore this noise will come into the measurement, because the noise doesn't cancel. The only thing that we reject as common mode is the sum of intensities of the 2 inputs. But the noise, the detector noise, and if we want to do a quantum measurement, that probably means that we need detectors that are very quiet. And indeed, that is the case. And if you want them very quiet, then they cannot be too fast. Well, okay. Now, all of this was classical, but you already know what we need to do if we want to go quantum. Just put hats on everything. Now, the only big questions, so everything is really the same. You put here, the only question is how do I implement the local oscillator? Because the local oscillator has to be something that's very stable with a very stable phase. And for this we need the coherent state. What we're going to put here is the closest thing that we can find to a good local oscillator. And the point is that a coherent state with a large amplitude is very much like a very good local oscillator. And then let me show you that what comes out in this case is indeed, let's do a quick calculation of, so what I'm going to tell you is, so if I want to talk now about the quantum homodyne, all I need to do is now to give you a quantum analysis of what happens here. Okay? The device is the same. It does the same thing. We want to do just to discuss whatever happens within this here, around this beam splitter, and in those detectors, what is happening. Let's do this quantum mechanically. So if I want to talk about quantum homodyne, then I would say, look here. Here is indeed mode 1, and here is mode 2. This is where my field comes in. So there is some state psi, which I don't know what it is. Here, there's my local oscillator comes. So this is a coherent state of the local oscillator. And we said that alpha is large. Alpha absolute value squared is much, much larger than 1. In the sense that we will be able to dismiss some of the things. Now, we know, so here there is a mode, this is mode 1, and there's a, like a field operator associated with it, A1, and here there is A2 associated with this one, and we know what we have here, and then eventually we detect. So we have 2 detectors, and here I have 1 over square root of 2, A1 plus A2, and here there will be a minus. And here we detect, this is A3 equals this. And here there's the minus of them. And what do we do? This measures the intensity, which is proportional to what? To counting the number. So here we have an intensity which is proportional to A3 dagger A3. And here we will have an intensity that goes like, or a current that is proportional to A4 dagger A4. This is, I'm counting, now this is an important point. Actually, I don't want it to be proportional. I want it to be equal. What do we mean? Remember what happens at the detector? Light generates photoelectrons. Now this was when we were talking semi-classically, but now we talk quantum mechanically. And now there are photons hitting this detector and photons hitting that detector, and they are generating photoelectrons. It is important that the quantum efficiency will be 100%. You want detectors that from every photon that hits them, generate a photoelectron. Why is that important? Because if they don't, it's like a random process that adds noise. You know, if light, you want to detect what is coming here to measure the intensity of the light. You don't want to measure the photocurrent. You want to measure the intensity of the light. If you're missing a photon here, then maybe at the same time you didn't miss it here, and you're generating noise. We'll discuss this in a moment. That will be clearer soon. Okay? So, but for now, let's assume that I'll just even bluff and just say that this is just it. This is what we measure. you know, this is a theoretical course, and I'm a theoretician, and for me it's no problem to write. I measure the number. How do you measure the number? You sit there and count them? What?
Didn't you say last class that you were an experimentalist?
What?
Not anymore.
But I'm incoherent today. Okay, so what we will be assuming that indeed every photon is generating a photoelectron. And therefore, in what I do here, I can count every photoelectron that is emitted. All the electrons, I can measure them precisely. I have a precise current measurement that does this. And what I will have here is this, A3 dagger A3 minus A4 dagger A4. So let's calculate this. So let's calculate this operator and understand the relation between this operator to the operators A1 and A2. Yes. And then we'll make some simplifying assumptions. And eventually we will see that this is measuring exactly the X operator or the Y operator. What time is it? Okay. So, yeah. So we wanted to say, okay, so we know that A3, what is it? It's 1 over square root of 2 times A1 plus A2. And what is A4? Well, that's 1 over square root of 2, A1 minus A2. And so, yeah. If I want to talk about A3 dagger A3, that is, there's going to be a half, and then there's A1 dagger plus A2 dagger times A1 plus A2. And of course, this is, the half is out. A1 dagger A1 plus A2 dagger A2 plus A1 dagger A2 plus A2 dagger A1. Now, what will happen about A4? The intensity of A4, everything the same except this minus. So if I want to, so this is the only thing that flips sign. So A3 dagger A3, well, there's a half here and there's a half there, and when we take minus A4 dagger A4, the half goes away, and what we have is A1 dagger A2 plus A2 dagger A1. Now, so this is the measured operator. Now, look, if I could say that A2 is a number, if I could replace A2 by a number, and even the same number, okay? Remember I told you that I have a local oscillator. A2 is the local oscillator mode. Okay? So if I can just replace A2 by a real number, I want this to have alpha local oscillator times A1 dagger plus A1. This is X. This is indeed the operator. If this was a local oscillator, and this is a local oscillator, not a local oscillator, a harmonic oscillator. If this field was a harmonic oscillator, and as we know it is a harmonic oscillator, then this is what we want. So we want to be able to measure X. In order to say that I want to measure X of this input, right? So in order to do that, I want to replace A2 by a real number. And by the way, if I want to measure Y, I want to replace A2 by an imaginary number, right? If this, because then the dagger would be the minus sign. Yeah. So, and here comes the point that indeed, if I have if in mode 2 we have a strong coherent state, then okay. So this operator that we have, no, I didn't want to do that yet. So this is what we would like to have. But this operator that we have, it operates on 2 modes. And so now we have here, right, the state that we have, the real state that we have, psi total. This is the mode psi in mode 1 and times the state in mode 2, which is the local oscillator. And what's nice about this, and now we can say that, well, what do I have here? Is this operator that I have here. I would like to say that, look, then this A1 dagger A2 plus A2 dagger A1 that operates on this psi and alpha local oscillator, then look, almost everything is fine. When I'll operate with this, it operates only on the alpha local oscillator and generates alpha. And this one, well, that's a little bit annoying because I cannot operate it. When I operate the creation operator on the coherent state, I don't get exactly the same. But come on, the commutation between those two is just 1 unit. So, so then I want to say that what I'll get is, if this is sufficiently large, then this is alpha local oscillator. It is replaced exactly. And this is approximately alpha local oscillator star. And really, it's pretty close. So and for a classical case, and then what we have, therefore, is alpha local oscillator times A1, in this case dagger, plus alpha local oscillator star times A1. And now this operates just, and this is an operator that operates just on psi in mode 1. And this is nearly, so this is almost what we need. So the only approximation that we did here was to assume that operating this on the alpha local oscillator is also returning nearly a number. So we're going to talk about coherent states in a moment and explain why this is justified. But then you see now that how a quantum homodyne is basically just a classical homodyne. You just treat the element of the beam splitter, which we call the mode mixer, but this is not where the mixing, the multiplication happens. That's what's misleading maybe, because in radio frequency, when we say a mixer, we mean a multiplier. And in optics, when we say a mixer, we just mean the beam splitter, which, yeah, it mixes the modes, but it doesn't do any nonlinear effect. The nonlinearity comes in the detection. Again, another inconvenient common expressions. The detectors are considered linear. Well, they are linear in intensity. So if you have a good linear detector, it's linear in intensity, but it's not linear in the field. No detector of light is ever linear in the field. So all detectors of light, even the linear ones, are generating something that is highly nonlinear. They detect the intensity and not the field. So they are doing something squared. Okay. And as we said, so now it's clear that tell me what the phase of the local oscillator is, and I'll tell you what you're measuring. When alpha is real, real, then you're measuring x of the x1 times alpha. And if alpha, local oscillator, is imaginary, then you'll be measuring y of the input times alpha. So, yeah. End of discussion of the quantum homodyne measurement. And I think now is a good point to have a 10 minutes break and come back to remind you a few things of the coherent state, which will explain why this approximation is well justified. I'll remind you, this will be quick because I assume that you saw this maybe once at least, that the coherent state is nothing but a shifted vacuum. And so I'll remind you of the properties of the coherent state. And then, so that will explain why when we think of a strong coherent state, we really think of something that is the most classical element we can think of, and why when the coherent amplitude is very large, then it becomes really classical. And what's the relation of that to vacuum and all this in 10 minutes. And after that, there will come the really fun part, because then we'll start thinking about squeezing. תואר ראשון משהו, אז בטוח שמעתם אותי שורק. Okay. So, yeah, let's say a few things about the coherent state. The most classical, and you will understand why we call it the most classical state there is. So, well, you know that the coherent state is an eigenstate of the annihilation operator. So A operating on the coherent state alpha is alpha times alpha. This is the definition. Now, can we have eigenstates of the creation operator? Unfortunately not, because the creation, you know, there's no way to create vacuum. I can annihilate photons. No, the space is unlimited from above, but it is limited from below. So, you know, if I had like, you know, a dagger operating on alpha is not alpha star alpha. We'll see in a moment why. So this is the property that defines the coherent states. They are eigenstates of the annihilation operator. And if you remember, the annihilation operator is what replaces the complex amplitude. And therefore, those are states with a well-defined complex amplitude. As we mentioned, it's not completely well-defined because A is not a Hermitian operator, and A dagger don't commute. But okay, so and then I can ask myself, okay, so what is that coherent state? So I'll say, well, let's write it as some superposition of number states. And I said that what we need is that if I want to operate with A on alpha, well, I know what that is. That is this sum over Cn A operating on n. And what A does to n we know. It just shifts it down by 1. So this is sum over Cn square root of n minus 1. This is what it is. And yeah, this starts from 1 to infinity, where this starts from 0 to infinity. Because the vacuum, it annihilates. And then that means that, or in other words, if I want to compare coefficients here, then clearly I have a recurrence formula that says that Cn equals what? Cn plus 1 times square root of n. True? Yeah. Square root of, I think, n plus 1. What? I think that would, no, that's fine. That's actually fine. And this should, of course, oh, I'm sorry, let's say that this must be, so I can write this, let's shift it back to start from, to have this be 0. So this is sum of Cn plus 1 times square root of n plus 1 times n when this goes from 0 to infinity. And this we want to be alpha times sum from 0 to infinity Cn. So what do we say? What we have then is that alpha Cn equals Cn plus 1 square root of n plus 1. And this is actually correct. So this, we have some recurrence formula. That tells us what are the coefficients of coherent state. So Cn plus 1, tell me what your eigenvalue alpha is. And this is alpha divided by square root of n plus 1 times Cn. Or, of course, this comes back to what you were saying. I could write Cn equals alpha divided by square root of n, Cn minus 1. So, okay. First of all, I want to say something. What about alpha equals 0? Well, that's simple, by the way. This state is the state that you know very well. Alpha equals 0. If alpha equals 0, then this A operating on alpha generates 0. We know a state which does this. It's called vacuum. So alpha equals 0 is just vacuum. So the vacuum state is a coherent state. So vacuum is, the vacuum is a coherent state with alpha equals 0. So, and you can see also here that, well, yeah, it will work. But yeah, all of those would be 0 except for the first one, because alpha equals 0. And yeah. Okay. Now this recurrence formula is very simple. And we can say then that Cn equals what? Alpha to the power n divided by square root of n factorial times what? Times C0. And C0 is the coefficient of the... So this is defined by normalization. So the coherent state, we can write it now. And this is decided by normalization. So I can say then that the coherent state is indeed the following sum. Let me write it. E to the minus alpha squared half. This is the normalization part. Times sum over n alpha to the power of n square root of n factorial n. So now we know how coherent state looks like. Okay. And basically, now we can do almost any calculation we want about the coherent state. For example, we can ask ourselves, what about two coherent states with different eigenvalues? So I'm asking about something like orthogonality. Are two different coherent states orthogonal? The answer is no, but almost. So orthogonality, then I'll put it in bracket like this. And so I'm asking myself, what is, suppose that I take alpha and beta, two coherent states like this. And I'm asking, what is this? So, well, now you can see that, okay, there's going to be e to the minus alpha squared and e to the minus beta squared. So there's going to be this beta squared over 2 here. And then that's outside. Then there will be a sum of n and m. What? Alpha to the power n over square root of n factorial times beta to the power m square root of m. And then here what? N m. Actually, I should be careful. If this was like this, then there's a star here. But we know what this is. This is simple. This is delta n m. And so the double sum becomes a single sum. And here there's a m factorial, of course. And what we will have now is we'll have here this equals this prefactor that I don't want to copy times sum over n alpha star times beta to the power of n divided by n factorial. What is this sum? This is e to the power alpha star beta. So what we will have in the end is that this alpha beta equals e to the minus what? Well, then I'll tell you this. Alpha minus beta absolute value squared divided by 2. That means that if alpha and beta, so alpha and beta should be what? Not different by more than 1. So this falls like a Gaussian. So when alpha and beta are different, this falls like a Gaussian. And the difference can be of order 1. So look, those are complex numbers, of course. So they can have a so if alpha minus beta is larger than 1, then they are practically orthogonal. So if you have two coherent states that are close, now notice this is a complex number, so they could be maybe of the same average photon number but different different in phase. Now, okay. Now, if you remember, of course, so they are orthogonal. So now I want to say that alpha is a shifted vacuum. Now, we want to prove this, to explain. Now, I already told you that the vacuum is a coherent state. And I want to tell you that, to show you that all coherent states are just vacuum, just move it. How do you move the vacuum? Well, you put it in a box and you move it. We'll discuss this, but that's really actually simple. If you remember, I can say that N, what is this? It's operate with a dagger N times on the vacuum. Well, and now you need to normalize by what? Every time you operate this, you get a square root of N. So, no, this one becomes so, and then divided by, I'm sorry, this is a dagger N times divided by square root of N factorial. And if we remember this and we put it in here, then we get that the coherent state is what? Is some kind of an operator, e to the minus alpha absolute value squared times sum of what? Alpha to the n, a dagger to the power of n divided by n factorial, because there's square root of here and square root in there, operating on the vacuum. Now this is an operator that operates on the vacuum. Now again, if you see here, this is just an exponent. This is the sum, the series definition of an exponent. So that means that the state alpha is what? Is this e to the minus absolute value of alpha squared to the power of 2 times e to the what? To the alpha star a dagger. This operates on the vacuum. No reason for a star. Nothing special about him. He's not a star. Okay. Now I want to tell you, look, this is a shifting operator. Now we need to understand shifts in what. What does it shift? Oh. It's not ugly. Okay. So I want to do a little bit of a massage here. To show why this is actually a shift operator. But so now I want to show you what the real shift operator is, and then show you how it relates to what I wrote there. I want to claim that the shift operator d of alpha is this operator, e to the minus alpha a plus minus no, sorry. Come on. E to the alpha a plus, sorry, minus alpha star a dagger. Just to make sure that I'm not, yeah. Now, I'm claiming that this is a shift operator. Let me show just one thing. Let's take for a moment alpha to be a real number. Okay? So let me see if I want here. Okay, yeah. So assuming that alpha is a real number, so okay, this is for alpha real, what will it be? That will be e to the alpha times a minus a dagger, and that is nothing but e to the, remember that a minus a dagger is I y, or if this was a harmonic oscillator, then it's IP. Okay? So this is like I alpha P. Then that's the operator, P. How do you shift a state in, if I want to take the state x1 and shift it to a new state at x1 plus x0. What do I do? To shift the state, there is an operator that will do this. What is it? Well, in Fourier domain, it's e to the I p x0. That is what shifts you. This is what we had before. Where was it? That, you know, multiplying by e to the I omega t is shifting the frequency. Or multiplying by e to the I omega x0, t0 will shift the time. So this is that operator for alpha real is a shift, that's a shift in x. It takes your state from x 2x plus alpha. And clearly, if alpha was imaginary, here, alpha was imaginary, then this would have been a shift in P. Why? Because if alpha was imaginary, then I would have here alpha times A plus A dagger. So then instead of P, they would have here an X. And generally, it shifts us in this complex phase space. So it takes you in this, in phase space of real and imaginary, field. This alpha is the amplitude, and this operator shifts you from 0 to position alpha. If alpha is real, it takes you from 0 to alpha, and it shifts you in x along the real axis. If alpha is imaginary, it shifts you in P. And in general, it shifts you anywhere. If alpha is a complex number, it will shift you anywhere. Ask if you don't understand. Because I have the ability to make people believe that they understand. So, especially when I'm incoherent. Okay, so now we understand why this is a shift operator, but why is this that? Those two operators are not the same. There is some relation here, but that's not the same. So maybe I wanted.
I mean, it's the same as
I think, yeah, just so that things will be convenient. Let's put here the star. Just so this will be that. But where we put the star, that's up to us, of course. Now, okay. So, but now I need to remind you that what is e to the a plus b? If you have and a and b are operators, well, this is e to the a times e to the b times e to the commutator half, the commutator of a and b. Have you seen this? Have you ever seen this? That is, if a commutes with the commutator of, if this, okay, so this is actually a well-known theorem of quantum mechanics. So now we're going to use the fact, which is a theorem which says this, and that is true if the commutator of A and B is 0, and so is the commutator of B with the commutator of A and B. It's very quick to prove. I'll just mark how it is done. I can say that, look, what is e to the a? Well, that is, of course, sum over a, the power n, divided by n factorial. And same goes to e to the b and e to the a plus b. That is then sum over a plus b, the power n divided by n factorial. Now, I want to ask. So, of course, with numbers, you know that, and e to the a, e to the b, that is, well, that's sum over n and m. That's a double sum. A to the power n, b to the power m, divided by n factorial m factorial. No.
Yes.
No. Yes?
Yes.
Yes, that's true. Okay. Now, we need to somehow go from here to here. Now, the point is that when we open this a plus b to the power n,
They won't be perfectly ordered.
what?
They won't be perfectly
They won't be perfectly ordered. Right. There will be here a to the power n, and there will be here a to the power n plus 1, n minus 1 times b, but there will also be cases where the b will be sitting in between, because this is a plus b, and when you open this, you'll have all orders. So you'll need to use the commutator. And now we say, okay, the commutator is non-zero, as indeed the case. If the commutator is non-zero, then clearly, if the commutator is 0, then everything's fine. E to the a plus b is e to the a times e to the b. For operators as it is for numbers. But when the commutator is non-zero, then things become complicated. But there is a simple case. And it is indeed our case. Why? Because what is the commutator of those two operators? They don't commute. But their commutator is 1. It's just a number. So that means that everything commutes with a number. So the next commutators, the higher order commutators, they're all 0. So in our case, the first commutator, the commutator of A and B is 1. Well, it's not 1. It's alpha star times alpha, so it's alpha absolute value squared. But the higher order commutators, they're all 0 because this is a number. So this is indeed the case that we have here. And then by doing this series and carefully calculating, doing the commutations, the number of times that you need them, and you'll end up with this. So this was just to show you what's the problem and how it is somehow solved. But now you need to believe me on this, and if you believe me on that, then that means that what we have here is, then in this case, using this, we have that, where do I write it? I'm not using the space very well. So from using here,
You can probably erase what you want on the right.
I can do many things. So we can write that e to the alpha star a minus alpha a dagger is like what? Like e, so let's take first this one, e to the half, because this is just a number, you can put it anywhere. So e to the minus alpha absolute value squared divided by half. So half, and the commutation relation between these two guys is, because a dagger is 1. And times e to the alpha a dagger, but minus, but in this case, times e to the alpha star a. Now you can put them in any order you want. Okay. Why did I do all this? That was a good reason. Yes. So, yeah. Okay. Sure. Now, if I operate Now, operating this on vacuum is simple, right? It annihilates vacuum. The only thing that remains is this 1. If you think of this again as a series, all the elements of that series operating on vacuum do nothing, and only the first term leaves 1. So when you operate on vacuum, this operator, which we agree that is the shift operator, and this operator that we got from the series are the same. So yeah, when we operate on vacuum, this shift operator and this operator, they do the same thing. If you don't understand why, then tell me.
I understand why, but I don't understand what is the physical meaning.
Ah, okay. So here comes the physical meaning. As I told you, let's do another quick calculation. So that means that if I have this operator d of alpha, so if I take d of alpha and operate it on vacuum, I get alpha. Or I can say something like this. If I have the operator A and I do something like this, d dagger of alpha times d of alpha, this is just A plus alpha. What did he do? Okay, what did I write here? Basically wrote here d to the alpha, we know what it is. Let's use that convenient one. Alpha, let's assume that alpha is a real number. Okay, so alpha times A plus A dagger. And I have here A. What? And then here, what? A minus. Yeah. And here we'll have d dagger of alpha. But d dagger of alpha is the dagger of this. What is this? Well, it's e to the dagger. This is the minus of what's sitting here, right? So e to the minus alpha times a minus a dagger. Now I'll put a dagger on everything, and then this one will get a dagger first. So yeah, I mean you can do things like this. I mean there are ways to calculate things like this.
Formula for this, no?
Yes, there is a formula for this, but this, you know, what you can do now is expand this into a series and expand this into a series and try to calculate what you get. But this is what you get. So now you need to just believe me. And what you have out of this is a plus alpha. Where does this shift come from? Well, it comes from the fact that, you know, if everything would have commuted, I mean, if this could commute with A, then those two would have annihilated each other, and then just A. But this is a result of the non-commutativity of A and A dagger. I cannot just commute these two and have the two exponents annihilate each other. And this is what, but eventually, this does give this. This is again something that uses a well-known trick, which is to say that e to the b times a times e to the minus b equals what? equals A plus the commutator of A and B plus, sorry, the commutator of B and A, not that it matters much, but plus a commutator of B commuting with B and A plus add commutators more and more. That's also, this is the formula that is used to express this guy. But in any case, what is important to remember is that I just told you, look, if I operate with this operator on the point is on any state now. You know, if I operate with this on the vacuum, I generate alpha. I told you, look, this is a shift. More than this, if I look what this thing does to the state, now, or let me ask you in a different way. Suppose that I take this and operate on state that has an eigenstate beta. It will shift it to alpha plus beta. And it will be an eigenstate of what? Well, it will be an eigenstate of A with a value of alpha plus beta, or it will be like shifting the A by the shift. You know, I could say, look, I could say what I did was to shift the vacuum to alpha, or I could say, no, what I did was to shift the operator to A plus alpha, and I'm still operating on vacuum. You still get the same, everything's the same. So, you know, if I'm operating this on vacuum, I'll get alpha times vacuum. So it will be an eigenstate of this operator with an eigenstate alpha. So I can think of, so what I'm doing is either shifting. Now, eventually, what we want to say, okay, and this is also an important result. So this is, so that is the, that's the proof. It's not really the proof, but it's the beginning of the proof. I mean, you see where it comes from. So unfortunately, today I am a theoretician. And now let's try to understand, let's make one last calculation. This is something that we already know. What's the average number of photons? So n, the average number for an alpha, average intensity. Well, that's just count the photons. So that is just alpha, A dagger A alpha. And this, as we know, and now that's just Brian Kett tricks, A operating on alpha is alpha, A dagger operating on alpha to the other side. It generates alpha star, so this is just alpha absolute value squared. So the intensity of a coherent state, the average intensity, is the intensity of alpha. What I want to say is, look, this value alpha is nearly, it's as close as we can get to the complex amplitude of the field. The average intensity is alpha squared. Let's ask ourselves, what is the uncertainty of n squared? Well, that is, as we know, this is alpha times A dagger A dagger A alpha minus n average squared And this, as we know, is just, so this is, well, what can I do? Well, it's easy. I can operate this once here, and I operate this once here, that's fine. But then I have them in the wrong order. So what do? I use the commutator to get them in the right order. So that will be, we will have alpha absolute value squared times what? Times alpha a dagger. Alpha minus what? Alpha absolute value to the 4. It was squared, by then we had it squared again. Now this is 1 plus a dagger a, using the commutator. And a dagger a, I know what to do with. So then this will be, a dagger a will give me another alpha squared. So I'll have here alpha to the 4 plus alpha squared minus alpha to the 4. So the alpha to the 4 goes away. And delta n squared is alpha absolute value squared, which is just n average. The average of n, or delta n goes like square root of the average. So those were, so, okay. And even more, let's do another thing. And that is to measure what is the average x. What is the average x, which is basically alpha operator x alpha. Well, that's easy. We're going to have x is, so we have here alpha, and then what? A plus a dagger times alpha. Well, and of course, the a here will operate to the right and give me an alpha, and the a dagger here operating to the left will give me an alpha star. So what we'll have is alpha plus alpha star, which is the real part of alpha. And where did all the factors of 2 went? At the same place where the half went, and eventually they canceled each other, and they came like. And of course, if I ask what y will be in this case, it will be just the imaginary part of alpha. So you can see that slowly we are gaining the understanding that alpha, at least in terms of the average case, the average alpha, the alpha is related to the intensity, the total intensity. The average x is related to the real part of alpha. We can ask ourselves, what is the uncertainty of x and what's the uncertainty of y? So we can ask ourselves, what is x squared minus x squared? I'll tell you what it comes down to. It's 1. I mean, you can calculate, of course. I mean, it will be this. A plus a dagger, and we will have to open the brackets, and we have to operate with the commutators carefully. And I'll just tell you what happens. This is just 1. So the uncertainty of x is of the order 1. The uncertainty of y is of the order 1. And alpha is of the order n, or square root of n. Alpha squared is n. So that means that there is an average x on this state. It is the real part of alpha. And it has an uncertainty, which is rather small if alpha is large. Okay? The uncertainty is constant, is independent of alpha. And it should be. If you remember, what is the uncertainty of the vacuum? The x uncertainty of the vacuum, we calculated it. It was 1. Maybe it was half, but forget it. The units are the same. So it's the same. So what I want to tell you is this is independent of alpha. That's the important part. And therefore, it is for any alpha as it is for the vacuum, because vacuum is an alpha state. Alpha equals 0. And in that sense, this is a shifted vacuum. You take whatever properties that the vacuum has, and you just move it to alpha, where alpha is the field. And so that's why I say, look, this is delta x squared, and the same I can do for delta y squared, and it comes out as 1. And that's independent of alpha. Nor this, and then we take this guy out. So as far as we went by so far now, what time? Oh, I wanted to say something about the Wigner function. Okay. So really, then that means that, you know, if I ask myself, I'm talking about a quantum state and I'm trying to relate it to what I know from classical electromagnetics, and classically I had this complex field where this was x and this was y, and the state was a point here. Now almost everything is the same. The average x is indeed this, if this is alpha. The average x is the real part of alpha, and the average y is the imaginary part of alpha. The intensity is alpha absolute value squared. The problem is that there is some uncertainty related to x, and there is some uncertainty related to y. And there is some uncertainty related to the intensity. And you get this by assuming that, look, there's some, here there's a blob. If you remember, we also said that two states, they are orthogonal only if they're far enough. Only if e to the minus, alpha minus beta, if alpha minus beta was sufficiently larger than 1. Why? Because alpha and beta, they're not points in the complex plane, they're blobs. And they look, and if you remember, what are they? They are a shifted vacuum. Vacuum is the same thing around 0. And what is vacuum? It's a Gaussian. It's a Gaussian in X. By the way, it's also a Gaussian in P. Yeah. But so that is, and here, this is delta x, which is of order 1. And here, there's delta y, which is of order 1. And there's an average x and average y. Yeah, I don't want to write more, but and yeah, so in this sense, does this give you more of a physical meaning to it? There is a coherent state at alpha equals 0. That's the vacuum.
Yeah.
Every coherent state is the same. They're all just shifted versions in this complex plane. They all have the same uncertainty in x and in y, and they all actually are also transform limited, not transform limited, uncertainty limited. Because delta x squared, delta x times delta y is 1, which is the limit, the Heisenberg limit Well, yeah, where is h bar squared divided by 4? But, yeah, all of those are fine. No. Is it 1 or a half? I don't remember, but it is what it should be.
It's a number.
Yeah.
That's close enough.
It's a number, and you can always normalize so that it will be what you. Okay. So, and by the way, what happens to alpha as we evolve in time? So let's think about this. If I had the state alpha at time 0, psi of t equals 0, was this. What is psi of t? Well, now I assume one thing is that we assume that what we develop according to is the harmonic. This is a harmonic oscillator, right? So psi of t is what? It's e to the I h t times psi of 0, right? But what is e to the I h t?
Depends on what's your Hamiltonian.
Yeah, but Hamiltonian is a nice Hamiltonian. What? Yeah. So our Hamiltonian is, well, what is it? It's h bar omega times a dagger a plus half, right?
So there will be some constant phase shift and then some operating points that we need to think about.
Yeah. Okay, but here we probably want to stop. But, guess. What happens to a classical state?
So it just rotates?
It just rotates. A classical point in phase space rotates around. What happens to a coherent state? The same thing. So actually, so what we will have here, we will have e to the I times h bar omega divided, of course, by h bar, so the h bar went away, times a dagger a plus half, and this operates on the state alpha. Now, there are many ways. Oh, and there should be a t, of course, here. Now, it's very simple. It's really simple to show because the commutator of a and a dagger is 1. So what do? You take this. You have here e to the I omega t times the exponent of this. And then you write the exponent as a Taylor series. And then you remember that there's the problem of, you need to commute sometimes, but the commutator is a number. So every time, once you commute once, it becomes a number. So the commutator of commutators is not a problem. And you'll end up finding that this will be, and every time that A operates on this, you get alpha. And what will you get? Believe me that it will come out. You'll get alpha e to the I omega t alpha. Sorry, no.
Yeah.
I'm sorry, no, that's not what I meant. No, there's no alpha out. It becomes this, alpha e to the I omega t inside. You look at this state and you see that what you have is an operator that what you generate by this is a new coherent state, with a different coherent value. You shift. So indeed, what happens is that a coherent state in phase space is really like a blob. And if this was the amplitude, what it does over time is just it rotates around.
I think there might be a simpler way to see it.
There might be. There is.
If you open your Hamiltonian into two different one with the half, one with the A dagger A, and then the coherent state is the eigenstate of A dagger A. And then
You're right.
that half of the Hamiltonian doesn't do anything just by how states develop in time.
It sounds like you're right. Yeah. But so a coherent state has an uncertainty which is independent of alpha and also independent of time. It remains a coherent state, remains a coherent state. It's not an eigenstate of the Hamiltonian. It changes. Alpha changes with time, but it doesn't change the fact that it stays a coherent state. It's not the same coherent state, but it is a coherent state. And this coherent state changes its eigenvalue and just moves around. So all of those show you how alpha is the most classical state you could have. And why indeed when alpha is large, you can disregard the uncertainty in x and uncertainty in y, which relate to some uncertainty in intensity or uncertainty in phase, but they're small compared to the average values that can be as large as you want. So that's why, so there are several reasons why this can be considered a classical state. That is because it's independent of alpha, and it's a constant, and yeah, we said everything. So given the fact that now is about the end of our meeting, there is one thing that I want to show you then. And there's one thing that we were missing. I was relating, what did I do? I calculated here the second moment, the uncertainty, the fluctuation of x. Okay, I can relate it to some uncertainty here. But how much is this a reality? Can I really generate something that resembles the phase space distribution that we had for a classical state? I mean, if I have a I said, look, a classical field is a point, and if I don't know if there is some uncertainty on that point, then it becomes a blob, because it's my problem. I just don't know. Every time I turn on the device, I'm a bad experimentalist, and I cannot make it every time the same. So there is some probability of having some value, and then I generate a blob. So classically, this blob, it's a probability density function of having values. And if I were to interpret this classically, I would say, look, you have a bad laser, and your laser, it has an average intensity that's not bad, it has an average phase that is about 0, but you have some phase noise and intensity noise, or you have some x and y noise. They're small, it's about 1, and that's it. Now this is actually, but you saw, I mean, quantum mechanically, what we did was completely different. There's no, there is a quantum fluctuation here, but there's no noise. The state is boom, alpha every time. It's just a quantum problem. So can we reconcile those two thinking? And can we reconstruct a phase space density in this way? The answer is that for coherent states and for vacuum, it works. So really, to think that what I have is a Gaussian blob centered at alpha of probability, it works. So we can fool ourselves. But only for those states. And that's another thing that makes them nearly classical. The fact that you can really think of them as being some classical uncertainty in your experiment. But this trick works only for those states. And I'll show you there's this give takes us to the field of quantum, like quantum probability distribution function, or quantum phase space. And we're going to discuss next week the Wigner function, which is the closest thing we could have to a phase space density, with the only one caveat that it can sometimes be negative. So it really looks like a probability density, and it's most of the times positive. And for a coherent state and for vacuum, it's completely positive, and then it's fine. It looks like a probability density function. But for other quantum states, it can be negative somewhere. So that makes it only a quasi-probability. All this next week. And I'm sorry for being incoherent today, but well. Which חומר?
מזגנים, זה החומר.